Hey everyone, we're going to be doing a practice for target 7.3. It's going along with the video that I just posted along with this one. So if you haven't watched that one first, please do so. It shows a thermite reaction, and I do give a description of the thermite reaction, but I'm going to go ahead and write it out here as well. So a thermite reaction is when you take solid iron, which, you know, is just solid, sorry, it's not solid iron, solid iron 3 oxide. Now, iron 3 oxide is Fe3 plus and O2 minus, so it works out to be Fe2O3, and it is a solid. This is also known as rust. So you take a bunch of rust, and you combine it with some solid aluminum. And when you do that, you can end up making aluminum oxide, Al2O3, which is a solid, and pure iron. But this actually gets so hot that it melts the iron. So this iron over here will be a liquid. Now, as far as the balance goes, it's pretty easy. 2 aluminums, 2 irons, and we are done. Now, the thing that we still have to do though is we have to start thinking about the energy here. So target 7.3 is all about tracking the energy in our system. So we're going to do that by making some LOL diagrams. So our LOL diagram here, we'll just do a before and an after for right now. Maybe we'll add more later. So we're keeping track of energy 2 ways right now. We are doing energy stored thermally and energy stored chemically. We are not worrying about energy stored in phase for right now. That's actually not a problem here because there's nothing here that's just going through a phase change. Everything here is going through some sort of chemical change. So that'll all be accounted for in the energy stored chemically. Later, if we wanted to cool this iron down to a solid, that would be something that would be included in phase. So let's think about what's going on here. This thermite reaction actually gets really hot, and it gets really hot during the reaction. So I'm going to go ahead and say that it started off room temperature and gets even hotter. Now, this is interesting because it's getting hotter even though we are not heating it up. We are not putting it over a fire or anything. A thermite reaction gets hotter than when you started, even though you're not warming it up. It's not like we applied a blowtorch to it or something. It actually even gets hotter than the blowtorch does. Blowtorch is not melting iron in that amount of time. So this is getting incredibly hot, and it's using energy that we are not putting in, which means that that energy must have already been there. So that energy must have been stored chemically already. Let's do nicer boxes, shall we? In fact, I could probably do actual like square boxes. Ooh, that's horrible. So these 3 added units of energy, here we'll actually add another one just to make it a little bit prettier. These 3 added units of energy, so see how we went up by 3, these 3 are new. Those 3 must have already been there, but those 3 must have been stored differently before. So that's what I'm going to show here is that these energy that was stored chemically is now being stored thermally. Now notice, there's no energy going into the system now. Energy that was stored thermally, or sorry, all this energy before, I see 8 different boxes of energy. Well, I still see 8 boxes worth of energy here. We didn't add any energy to this system. So this, if we were to describe this, this is before the reaction happens. And this is after the reaction happens. And this makes sense because this chemical reaction is happening and we are saying that energy is changing in that chemical account, right? We are taking energy that was stored chemically and changing it thermally. And remember, energy stored chemically is literally the energy stored when we are ripping atoms apart. When you take 2 atoms that were stuck together and you rip them apart, that stores energy. And we call this energy storage system energy stored, let's see if I can write it so you guys can actually read it, energy stored chemically. So here, and we actually look at the equation, we are ripping apart these irons and these oxygens. And when we rip apart those irons and the oxygens, that stores a whole bunch of energy. But we're ripping apart the irons and the oxygen, that stores a whole bunch of energy. But when we combine the aluminum and the oxygen back together, that releases a ton of energy. So overall, we start off with more energy and end up with less energy. Now, let's think about what happens later. So we're going to let this sit here for a bit. And as we let this sit here, it's not going to stay hot forever, is it? It will eventually start to cool down. So the way we're going to show that it starts to eventually cool down is I'm going to go down to just 3 boxes. You could do 2 boxes, you could do whatever. But we've definitely cooled down. Now, where did that energy go? Now, it is possible that we had another chemical reaction, but I don't think so. We don't have any indication that there should be another chemical reaction. There's no new lights or sounds or smells or anything. So I don't think there's another chemical reaction. So that means I think that the chemical thing should stay the same. Remember, ECH is the energy from combining these atoms together in different ways. Well, if we're not recombining atoms, this should stay the same. So where did that energy go? Well, that energy must have left the system. And if you watch the video, you can see it's obvious that energy is leaving the system, right? It's all glowing and spitting and everything. So energy must be exiting the system. So the requirements were to make this LOL diagram and then describe this as exothermic or endothermic. Well, look at our system beforehand versus afterwards. We start off with 8 units of energy. We end up with only 6. This must then be exothermic. Energy is exiting the system right here. This is an exothermic process. And if we have to put energy here, is this energy something we're putting in as a reactant, or is energy something we're getting out? We are definitely getting energy out. Now think about this. This energy here, why do we see it here, but we don't see it on this side? Well, the energy, it's the same reason here. This energy here that we're getting out exists over here too, but it's stored and it's hidden in a way we can't see. It's stored in the arrangement of atoms. Well, in the same way, this energy over here on the right is also over here. We just can't see it because it's stored in the arrangement of those atoms. So overall, if I were to give you a question like this, you would have to be able to show me 1, the LOL diagrams, 2, be able to describe it as exothermic or endothermic, 3, describe is energy a reactant or is energy a product, and 4, I could ask you some other question. I don't know. I'm sure there's all sorts of fun things that I could ask you. But this is an overview of what I expect for 7.3, these 3 sorts of things. Please do let me know if you have any questions. I'll be posting an evidence assignment for this later today as well. Have a nice day, everyone.